Good morning, friends, and I warmly welcome to you in the lecture of Mechanics of Solids. And we are discussing right now the series of bending stress in beams. Let us revise what we have learnt right now up till now in the series of bending stress in beams. We learned in the previous sessions about types of supports and types of beams, types of loads acting on the beam, determination of support reaction, plotting of shear force and bending moment diagram of statically determinate beams, concept of bending stress and section modulus, concept of bending equation and moment of resistance. The objectives of today's session is draw the bending stress distribution diagram and calculate maximum bending stress in a given section. That given section may be of symmetrical section, may be of unsymmetrical section. Let us revise. What is the meaning of bending stress? What is the equation of bending? And how to find out this bending stress? So if we take any section of a beam and consider the free body diagram on entire side, we find that there must be the three internal stress resultants at the section in general to maintain the equilibrium of the free body. These internal stress resultants are equal and opposite to the external effect of loads acting on the section, specifically named called. These three internal stress components are bending moment, shear force and the axial force. Here, in case of the bending stress, we are discussing the effect of bending only. Let us take one simple problem right now. A simply supported beam with the external loading which is given to us. Now, if we take a section XX right now over here, then my beam will be divided into the two parts, left part as well as the right part. So, if I will take considering the equilibrium, or I will plot the free body diagram of the left part, at that particular section, the three unbalanced or the internal force resistance will be developed. The first one is the bending moment, another is shear force, and third one is the axial force. Now this bending moment M causes the compressive force on the top fibers and the tensile forces on the bottom fibers. These forces develop the stresses at this particular section is called the bending stress. Hence, under the effect of the lateral loads, the beam bends and the longitudinal axis takes a curved shape. The beam produces an internal resisting couple to balance the bending moment due to applied loads. This couple is generated by normal compressive and tensile forces in the section. Now let us be understood what the bending moment does the beam. It causes compression on the face, one face, and tension on the other face. It causes beam to deflect. Clearly visualize that because of load it will deflect, but also the compressive forces will be developed on the top fibers while the tensile forces are developed on the bottom fibers. Now let us revise the bending equations that we developed or that we derived in the previous sessions. That is the M over I is equal to F over Y is equal to E over R. This is to be called bending equation, where M is known as the external moment applied, or it may also call the moment of resistance. I is the moment of inertia. F is the bending stress developed at a particular section at depth Y. E is the modulus of elasticity, and R is the radius of curvature. Now here, if I will simplify the equation is M is equal to F over Y into I. So if I will once again simplify this equation, it is F into I by Y, where I by Y term is referred as the Z. Z is nothing but the section modulus, is nothing but the I divided by Y. Now Section modulus, that is the Z, is defined as the ratio of moment of inertia of a section about the axis to the outermost layer from the neutral axis. That is, Z is equal to I by Y max. It is at most important for us to know this value of Z for known section like rectangular section, hollow rectangular section, circular section and the hollow circular section. So what will be the formula for the four sections that we have already been derived? Let us see. Let us be revised within shortly of 1 minute. Before that, strength of section M is equal to F max into Z. Here M is the moment of resistance offered by the section, that is, it is a maximum bending moment. Also, the moment of resistance offered by the section is maximum when the section modulus is maximum. Hence, section modulus represents the strength of section. It's most important word, that section modulus represents the strength of section. If higher the section modulus, the strength of section is high. If lower the section modulus, the strength of section is less. Now the formulas here for the section modulus. For rectangular section, the Z is equal to BD square by 6. For hollow rectangular section, that Z is equal to 1 by 6D bracket capital BD cube minus small bd cube, where capital B R and capital D are the outer dimensions of the section, while small b and the small d are the inner dimensions of the section. For circular section, Z is equal to pi by 32 D cube. D is the diameter of section, while for the hollow circular section, Z is equal to pi by 32 capital D bracket D raised to 4, capital D raised to 4 minus small d raised to 4, where capital D is the outer diameter of the section, where the small d is the inner diameter of section. Now, we are discussing right now today specifically the bending stress in unsymmetrical section. In case of the symmetrical section, the neutral axis passing through the geometrical center of the section. Please be careful, this statement is very much important. Let us be understood the statement on this tabletop. This given section is known as the rectangular section. Now, this is the CG or centroid of a section. Then this is the axis, XX axis, which is passing through the CG. Then the neutral axis passing through the geometrical center of the section. So this will be my neutral axis. So if this will be the capital D, then the available distance from neutral axis to this bottom fiber is capital D by 2. It is known to us. It is very easy for us to find out the neutral axis, and it is very easy for us to find out the section modulus precisely. Now next ahead, go PPT. Now, but in the case of the unsymmetrical section, such as L section, T section, some specific I unsymmetrical section where the neutral axis does not passes through the geometrical center of the section. Hence, the value of Y for the topmost layer or bottom layer of the section from the neutral axis will not be same. Hence, it is our most important, the first step is to find out this depth Y, either from the top or the bottom. Let us be understood this particular word on this particular tabletop. If I will take this L section, having the dimensions is there with us, we do not know what is the location of CG, whether my CG is over here, whether the CG is over, that we do not know, and that we have to find out by our basic concepts to find out the centroid. So for that I have to first find this YB or YT, and after finding these two values we have to find out the section modulus, that is I by Y max. What is Y max? Y max is nothing but the maximum between YT and YB. I think you have understood this one. Let us go ahead. Let us we take one problem and let us we discuss this problem over here and solve over here. A cast iron bracket of I section subjected to the bending. Important word, cast iron bracket. The word bracket which has been written, it means that it is the cantilever one end is fixed, another end is free, which is subjected to the bending. The dimensions of the I section is shown in the figure. Please see this particular figure. The dimensions visualized over here. The top flange width, this is to be called the flange. This is to be known as web. This is to be known as bottom flange. Here it is to be seen that the top flange which is of 200 mm, while the bottom flange which is the width available is 130 mm. Means this is unsymmetrical I section which has been given to us. If the maximum bending moment in the section is the 40 meganewton into mm, this is the subjected moment by this bracket, determine the maximum bending stress. And what is the nature of bending stress, whether it is the compressive stress or whether it is the tensile stress, that we have to determine first. Let us we solve this problem over here. So what will be the step? Intention is to find out the maximum bending stress, that is the M over I is equal to F over Y. M, which is known to us, which is given to us. I, indirectly given us by giving a section, means I have to find out the value of I. F, which is unknown, that I have to find out, and Y, which is indirectly given to us by giving a section. So the two parameters which is given indirectly, that we have to first find out directly by using the basic concept of CG. So first our step is to find out either distance between the neutral axis to the bottom fiber or the distance between the neutral axis to the top fiber, that we have to find out first. So the given data, an unsymmetrical I section, also the beam type is of cantilever. M is the 40 meganewton into mm, that is 40 into 10 raised to 6 newton into millimeter. Hence, to find the bending stress, we have to first find the location of the neutral axis, and based on that we have to find the section modulus. So let us find the CG of the section, and let Y is the distance of the CG from the bottom face. So what we divide? We divide the given figure into the three parts. Let us we see over here what are those three parts. Given I section is over here. So what we did, we divide the given I section into the three parts. Number one part, second rectangular part, third rectangular part. So we have divided this I section into the three parts, and we have used the concept of parallel axis theorem. I is equal to Ixx plus AH square. This fundamental theorem that we have been used to solve this one. So what we did, we found out I is equal to I1 plus I2 plus I3. I1 value for this, I2 value for this web, I3 value for this particular flange. Now how to find out I1? I1, which has been found out by using these basic principles of the parallel axis theorem, means one has its own axis CG XX. So if I will write down I1 is equal to 1 by 12 BD cube. So for this is my B, D is this one, plus AH square. What is A? A is nothing but area, that is B into D. What is H? I have to find out the value H. For that I must know the neutral axis. I know the YB. So H is nothing but YB minus D by 2. It is this one. This is my value of H. So to do this thing, it is important for me to find out first of all YB. To find out the YB, as I told previously, I have divided into 3 parts, 1, 2 and 3. So the formula is YB is equal to A1Y1 plus A2Y2 plus A3Y3 divided by A1 plus A2 plus A3, where Y1, Y2, Y3 are the distance of CG of that particular part from the reference axis. We have taken this bottom fibers is of reference axis. Let us see the same problem on this particular PPT. Now visualize this A1 is the area of bottom flange, that is the 130 into 50, that is of 6500 mm square. Y1 is the distance of the CG of area A1 from the bottom face, as the thickness of bottom face is of 50 mm. So 50 by 2, that is 25 mm is our Y1. A2, that is the area of the web, that is 200 multiplied by 50, 10,000 millimeters square. Why? The Y2 is the distance of the CG of A2 from the bottom face. Please refer what is the meaning of Y2 when we find out the CG on this particular tabletop. If this will be the CG for this web, then refer this one. This is the bottom face. This is my Y2. What is Y2? This available width, that is 200, divide by 2 CG, this is this distance, plus thickness of bottom flange 50. This is our Y2. If you want to refer, this is our Y2 on this table, on this PPT. So it is 200